is going to be part 1 for 4.4 derivatives of exponential and logarithmic functions. This is actually going to be our last lesson that we have on formulas of ways to take derivatives of things. And in chapter 5, we're going to get into some of the applications of those derivatives. So I want to look at this limit first, because there it says the limit as h approaches 0 of e to the h minus 1 all over h is equal to 1. So this is going to create a really interesting derivative, and I'm actually going to go back to using the x plus h formula to calculate what the derivative of e to the x would be. So the first thing we need to do is set this up. We have the limit as h approaches 0 of e to the x plus h minus e to the x, and then the whole thing all over h. So again, remember we would add this is the derivative from x plus h to x, they're h apart, so this is how we would set this up. If you recall your rules of exponents, anytime you multiply two things that have the same base, you add the exponents together. So we can actually take this and split this back apart. So this is equal to the limit as h approaches 0 of e to the x times e to the h minus e to the x all over h. So notice instead of having the addition, I actually split that apart so that I was multiplying two e terms, because again, it's the same base. Now on the top, they both have e to the x in them, so I can factor that e to the x out. And I'm actually going to write this up here. So this is the limit as h approaches 0 of e to the x times e to the h minus 1 all over h. Well, according to this first thing that we have here, this limit, the e to the h minus 1 all over h, that's equal to 1 when h is approaching 0. So this is really the limit as h approaches 0 of e to the x times 1. Well, the limit as h approaches 0 of e to the x, when you make h 0, there's nothing else to change. So that just gives you e to the x, which means the derivative of e to the x is e to the x. Actually, the derivative returns exactly what you started with. You do need to be careful, though, because just like with everything else, we're going to rewrite this as e to the u, because instead of just e to the x, you might have e to the 2x, or e to the sine of x, or e to the square root of x. So you do need to multiply by your du dx. You need to multiply by the derivative of whatever that u function is. But basically, the derivative of e is e. Okay, so here's our first example. We're finding dy dx if y is equal to e to the x plus x squared power. So dy dx is going to equal, anytime you're taking the derivative with an e, you always repeat what you have, and then you multiply by the derivative of the exponent. Since my derivative has, or the exponent has two components, I'm actually going to put this in parentheses. The derivative of x is 1. The derivative of x squared is 2x. So this is going to be 1 plus 2x. You can leave your answer like this, or you could actually rewrite it to put the 1 plus 2x out in front, and then times e to the x plus x squared power. So that is something that you need to be aware of as well. Okay, now, there are exponentials where instead of having e as your base, you might have some other number. That's what this formula goes through. It's actually identical to the e formula with this addition, natural log of a. So you're still, this is for any exponential, u would be your variable in this case. You're still going to repeat what you have, but you're also going to multiply by the natural log of the base. And we actually did that for the e formula as well. So really the e formula is the same thing, not dy. The e formula is the same thing. The only difference is natural log of e is just equal to 1. So that's why it wasn't necessary to put that. But if your base is like a 2, or a 5 or a 1/2, you would have to multiply by the natural log of that number. So this is for any exponential where the base is not e. Okay, so now we have this example, and this is going to require the calculator. You might have to just take my word for some of the calculations, since this is my new computer and I don't have my graphic calculator application installed on here yet. So at what point on the graph of the function y equals 2 to the t power minus 3 does the tangent line have a slope of 21? Well, if we're finding a slope, we need to know the derivative. So I need to find my dy dt in this case. So to take the derivative of the exponential, I'm going to repeat the 2 to the t, multiply by the natural log of the base, so natural log of 2, and then I would multiply by the derivative of the exponent with respect to t. Well, that's just going to be times 1. And then the derivative of 3 is going to be 0, or minus 3 is going to be minus 0. But what we're really asking ourselves is, where is this equation equal to 21? So I have natural log 2 times 2 to the t is equal to 21. You would have to use a graphing calculator for this. You can divide both sides by natural log of 2, but this is something where it's not going to be very pretty. So even if you do go through and do all the arithmetic for this, like you could divide, we have 2 to the t is equal to 21 over natural log 2. I would take the natural log of both sides. The natural log of 2 to the t is t natural log 2, and that's equal to natural log of 21 minus the natural log of the natural log of 2. And then you would divide that by natural log 2. So no matter what, you're going to have to use a calculator at some point. Even if you go through and do the algebra for this, natural log of 21 minus the natural log of the natural log of 2, the whole thing divided by a natural log 2, you can't find that out without a calculator. So your t value, you take my word for it, is 4.921. Now it does say at what point, so we do have to get the y value as well. And so you would plug the 4.921, and actually you might want to keep a couple of extra decimals when you're plugging in just to get an accurate value for y. But when you plug that back in for t in the original, you get 27.297. So this would be the point where it would have a slope of 21. If you're not comfortable solving equations that have exponentials in them, that might be something that you need to go back and work on through iExcel. Again, I took the natural log of both sides in order to get that t out of the exponent there. Because this section is a little longer, normally I split this apart into exponential derivatives like we did with e, and then with the base that's not e, and then I look at logarithmic derivatives in the next video. But I do want to look at least the derivative of natural log first, just because there's a lot of extra examples, and that'll make sure that the second part video isn't too incredibly long. Okay, so if you have u as some differentiable function, that has to be greater than 0 because you can't take the natural log of 0 or any negative number. The derivative of natural log is 1 over what you're taking the natural log of times the derivative of that term. So if you're taking the natural log of 2x, it'd be 1 over 2x times the derivative of 2x, which would be 2. In many cases with natural logs, you will be able to reduce and simplify your fractions, and you'll actually see that in example 3. Well, actually, maybe not example 3, but you might see that in the next one. One of the future questions that we go over. Okay, so with this one, we have some line that has slope m, It's going to pass through the origin and is tangent to the graph of y equals the natural log of x. And we want to know what the value of m is. So I know that one of the points that I'm dealing with is 0, 0. The other point that I'm dealing with is some other value. You could use x. I'm actually going to use a to keep things a little bit different. So I'm going to say, okay, let's say the x value is a for some other point. When I plug the a into this equation, I'm going to get back natural log of a. Now, using this information, well, how do we find the slope? Well, that's y2 minus y1 over x2 minus x1. So that's natural log a over 0 minus a over 0, which is natural log a over a. The other way that we have to find slope is to actually go through and take the derivative. The derivative of natural log x is going to be 1 over x times 1, which is just simply going to be 1 over x. Now we're evaluating this at the same point. So I'm saying, okay, this is where x is equal to a, so I get 1 over a. So if I set these two terms equal, so there's the derivative, there's the traditional slope, and I want to solve and actually see what value of a makes this true. Because again, it says I have my line that has the slope, so I'm saying that it's going to touch this natural log of x at some point a. That's why I found the derivative at that same point a. You could call it something different. You could keep it an x. You could call it a q. You could call it a p. Maybe a z. Whatever you wanted to call it. I chose a for this case. So if I'm solving this, both of these fractions have a in the denominator. So I really want to know the solution to this. 1 is equal to the natural log of a. Well, the natural log of what number is equal to 1? And the answer to that is e. The natural log of e is what's equal to 1. You could actually solve this by raising each side to the e. E to the natural log a is simply equal to a, and that's e to the first. So a is going to be equal to e. But that's not actually the slope, because if you recall, the slope is 1 over a, or natural log of a over a, which means your slope is going to be 1 over e. So this line is going to have a slope of 1 over e. If it passes through the origin, we know that point is 0, 0, and then it's tangent to this graph of y equals natural log x. So that's where I'm going to pause for now. I will make a second video that goes through the rest of the notes for 4.4. Again, if you're not confident with your exponential and logarithmic rules, that might be something to go back and practice in IXL. Reach out to me if you have any questions at all, and I hope that the material is starting to make a little bit of sense.